Good morning, students. Today we will discuss convex set, its examples and some problems based on normed linear spaces. So first definition is, what is a convex set? Suppose we have a vector space X and M is a subset of this vector space. Then we say that M is convex if for every two elements X and Y belonging to this subset M, the line segment joining X and Y that completely lies within M. Means we are taking the points X and Y, and this is the line segment joining X and Y. If this segment completely lies in M, then we say that M is convex. Now mathematically, the line segment joining the points X and Y is given by alpha into X plus 1 minus alpha into Y. This represents a line segment joining X and Y. Here, this alpha that belongs to the closed interval 0, 1. So this is a condition for a subset for vector space to be convex. Now let us see examples based on convex sets. So first example of convex set is that in a normed space X, every closed unit ball is convex. Closed unit ball means a ball with center 0 and the radius 1. Or we can say that this is a collection of all those elements of the norm space X such that their norm is less than or equal to 1. We prove that this closed unit ball is convex. So in order to prove this is convex, let us take two elements X and Y belonging to this closed unit ball. Now by definition, because X belongs to this closed unit ball, therefore by definition the norm of X is less than or equal to 1. Also Y belongs to this closed unit ball, therefore norm of Y that is also less than or equal to 1. So we have X norm less than or equal to 1 and Y norm is also less than or equal to 1. Now we have to prove that the line segment joining X and Y completely lies within this closed unit ball. So let us consider alpha belonging to the closed interval 0, 1, and let us consider alpha X plus 1 minus alpha into Y. Now we will show that the norm of this element that is less than or equal to 1. So let us consider the norm of alpha X plus 1 minus alpha into Y. Now here we can use the triangle inequality in norm space. So by using the triangle inequality, this is less than or equal to norm of alpha X plus norm of 1 minus alpha into Y. Now we can use the property of absolute homogeneous property of norms. So by that property, alpha X norm is given by mod of alpha into norm of X. Here also using the same property, this will become mod of 1 minus alpha into the norm of Y. Now because alpha belongs to the closed interval 0, 1, so alpha is non-negative, so alpha mod will be same as alpha, and also 1 minus alpha mod that is equal to 1 minus alpha. So we get alpha X plus 1 minus alpha into Y norm is less than or equal to alpha into norm X plus 1 minus alpha into norm Y. Now because norm X is less than or equal to 1 and norm Y is also less than or equal to 1, so this will become alpha plus 1 minus alpha, which is 1. So we have obtained the condition for the closed unit ball to be convex. So we have proved alpha X plus 1 minus alpha into Y norm is less than or equal to 1. So by definition, this belongs to the closed unit wall. So this proves that every closed unit wall in a norm space X is convex. Now our next example is every subspace of a vector space is convex. So let us take a vector space X and Y be the subspace of this vector space X. Now we have to prove that this Y is convex. So in order to prove that Y is convex, let us take two vectors X and Y from Y. Now let us take a scalar alpha belonging to the closed interval 0, 1, and let us consider alpha into X plus 1 minus alpha into Y. We have to show that this expression again belongs to the subspace Y. Now, because Y is a subspace of the vector space X, so it is closed under scalar multiplication and vectors addition. Now alpha is a scalar, X is a vector, so alpha into X, that is a scalar multiplication of alpha with vector X. So this belongs to Y. In the same way, 1 minus alpha into Y, that is also the scalar multiplication of the scalar 1 minus alpha with vector Y. Both these vectors, they belongs to the subspace Y. Now because Y is a subspace, so it is closed under vectors addition. So the sum of these two vectors, that will again belong to Y. So we have proved alpha X plus 1 minus alpha into Y, that belongs to the subspace Y. So this proves the condition to be convex. Thus we can say that every subspace of a vector space is always convex. Now next is a problem based on the normed linear spaces. We discussed the 4 conditions for a function to define a norm. Now here in this problem we will show that the condition norm x is equal to 0 if and only if x is equal to 0. This condition can be replaced by the condition norm x is equal to 0 implies x is equal to 0. And also in the next part we are to prove that the non-negativity of norm that can be obtained by using the last two properties of norm. Last two properties, absolute homogeneous property means alpha x norm is equal to alpha mod into x norm, and triangle inequality x plus y norm is less than or equal to x norm plus y norm. By using these two conditions we can obtain the non-negativity of norm without changing the concept of norm. So we are to prove these two parts. So in the first part, let us prove that the condition norm x is equal to 0 if and only if x is equal to 0 can be replaced by this condition. It means we are to prove that norm is 0 implies x is equal to 0. By using this condition, we are to replace it with this condition. So in order to prove it, we are to prove that if x is 0, this implies norm of x is 0. It means we are to prove that the norm of 0 vector is 0. Now let us consider the norm of 0 vector. Now 0 vector can be written as 0 into x. This 0 is scalar here. Because 0 is scalar, x is vector, we can use absolute homogeneous property of norm. By that property, we have mod of scalar into norm of the vector. So norm of vector x into the mod of scalar 0. Now mod of 0 scalar, that is 0. So 0 into x norm will be 0. So we have proved that norm of 0 vector is 0. So we have proved the condition x is equal to 0 implies norm x is equal to 0. Now next we prove the non-negativity of norm by using these two conditions. Now let us again consider the norm of 0 vector. Now 0 vector can be written as x minus x, where this x belongs to the norm space X. Now we can use triangle inequality. By using triangle inequality, this is less than or equal to x norm plus minus x norm. Here, using absolute homogeneous property, this will become mod of minus 1 into norm of x. Now mod of minus 1 is 1, so we get norm of 0 vector is less than or equal to x norm plus x norm. So from here we get 2 times x norm is greater than equal to 0. So this further implies that norm of x is greater than or equal to 0. So this proves the non-negativity of norm. Now next problem is based on bounded sets. So firstly, let us define what is a bounded subset in a metric space. If we have a metric space and we have any subset of this metric space, suppose the subset is A, then we say that A is bounded subset of this metric space if the diameter of A, that is finite. Now diameter of A means the supremum of the set of the distances between every 2 points of this set. dxy denotes the distance between the elements x and y. Here x and y belongs to the subset A of the given metric space. So we can say that a subset is bounded if the supremum of the set of the distances between every 2 points of the set, that is finite. Now there is a problem based on this definition. Show that the subset M of a norm linear space X is bounded if and only if there exists a positive number C such that norm of X is less than or equal to C for every X belonging to M. So let us take X be a normed linear space and M is bounded subset of X. Now by definition, because M is bounded, so diameter of M is finite. Diameter of M means the supremum of the set of distances between every 2 elements of M. Now in norm space, the distance between 2 elements x and y is defined by x minus y norm. Now because this is finite, so let us take this quantity as B. So we have obtained B is finite. Now we have to prove that norm of x is less than or equal to C for every x belonging to M. So let us take x naught be any point in M and let us consider x norm. Now let us add and subtract x naught inside this norm and using the triangle inequality. So by using triangle inequality, this will become less than or equal to x minus x naught norm plus x naught norm. Now this quantity is less than or equal to B from the equation 1 because the supremum of the set of the distances of the elements of M, that is B. So this will be less than or equal to B. Now B plus x naught norm, that is also a constant. So let us denote this by C. So we have obtained the first part, norm of x is less than or equal to C. Now let us do the converse part. Now conversely, we are given that there is a positive number C such that norm of x is less than or equal to C for every x belonging to M, and we are to prove that M is bounded. In order to prove M is bounded, we prove that diameter of M is finite. So let us consider two elements x and y belonging to M, and let us consider x minus y norm. Now by using triangle inequality, this is less than or equal to x norm plus y norm. Now this can further be written as, by using absolute homogeneous property of norm, this can be written as minus 1 mod into y norm. So we have obtained x minus y norm is less than or equal to x norm plus y norm. Now we are given that for every element x belonging to M, we have a positive number c such that the norm of that element is less than or equal to c. So we get x norm is less than or equal to c, y norm is less than or equal to c. So x minus y norm is less than or equal to 2c. Now let us take supremum over all xy belonging to M. So from here we get the supremum of x minus y norm where x and y belongs to M, that is less than or equal to 2c. Now 2c is finite. So we have obtained the supremum of the set of the distances between any two elements of M that is finite. By definition, this is diameter of M. So we have proved that diameter of M is finite. So we can say that M is bounded subset of the normed linear space X.